Welcome everyone. My name is Filippo Sanfilippo. I'm a professor at the University of Agder, and I am the leader of the research group called Artificial Intelligence, Biomechatronics, and Collaborative Robotics. This is our logo that represents our core research focus, the close interaction between humans and machines. Particularly, we call this kind of interaction human-robot teaming. In this presentation today, I will present our recent results, and the title of my presentation is Revolutionizing Prosthetics and Orthotics with Affordable, Customizable Open Source Elastic Actuators. This work is funded by the EEA Norway Grant within the collaborative project titled European Network for 3D Printing of Biomimetic Mechatronic Systems, Emerald project. So we are very glad to have the opportunity to participate to this international collaborative project. And here in this slide here you can see the summary of my presentation today. I will give a background introduction about the motivation and the objective of this research. Then I will present the novel design for an open source elastic actuator system for orthotics and prosthetics applications. And finally, I will show some experimental results with a demo. In this slide here, you can see a summary of our research topics organized into 3 different layers. The core layer is represented by carriers. These are robots that are operating in different environments. So we have robots that are operating in aquatic environments. We have robots with legs, robots without legs, like the snake robot, and flying drones or unmanned aerial vehicles. So these carriers can be equipped with add-ons that are represented by this upper layer. So the manipulators and grippers that can be attached to the robot are the devices that enable the robots to interact with humans and with the environment surrounding the robots. But the most important layer that we focus our research on is represented by the human-machine interface layer. So on this layer we have different sensors and different interfaces that are used to close the loop. So we have the human in the loop. Actually, the main focus of our research is to enable this concept of human-robot teaming. So here we have different interfaces for brain-machine collaboration. We have haptic devices. So the idea is to provide fully immersive, multisensorial feedback from the machines back to the humans. And this is very much framed within the revolution that is happening from an industrial perspective. So if we look back at history, we started having robots caged, so completely separated by humans, and then progressively we have liberated the robots to get closer and closer to humans, transitioning through human-robot interaction, human-robot collaboration, physical human-robot collaboration, and human-robot teaming. So human-robot teaming is our end goal, is much more than collaboration. So teaming means performing a task that neither nor the machine alone, neither the human can achieve by themselves. They have to team up. One of the main challenge in the current in this revolutionary process is the fact that most of the time in the current market and research landscape, robots are still using mostly rigid actuators, which are not safe for close collaboration. So elastic joints represent a possible solution to this, and this is our focus. So when we focus even more to prosthetics and orthotics applications, we can see that there is even more need for safety and for close collaboration. So particularly for prosthetics and orthotics, we want to achieve a symbiosis between humans and machines. So if we look at the current literature, we have identified a research gap, and basically there is a limited adoption of compliant actuators in prosthetics and orthotics devices, and there is then a need for a low-cost elastic actuator system with integrated sensors that can be designed in a way that is efficient from a cost perspective, and it is open. So this is exactly the gap that our group aims at filling. In this figure you can see the proposed device, and it is completely open from a software perspective as well as from a mechanical and electronics perspective. Everything, all the mechanics can be 3D printed, and the cost of a module is of around $100, including all the parts. Everything can be downloaded from our repository at our GitHub website. So here there is a more detailed representation of the proposed design. So basically we have a module that can be connected in a chain with other modules. So the module is composed of a lower joint and an upper joint. The core is the drive system, and then we have a base and a tooltip. So basically everything can be 3D printed and assembled, and the cost is within $100. An exploded view of the proposed design here. So we have a motor that is the core of our actuation system. It is a rigid motor, but the actuation system, the transmission system, makes it soft. So basically we have achieved a hybrid rigid soft actuation system, and what makes it soft is this torsional spring that is engaged when the joint is compressed. Then we have sensors at the motor side, an encoder at the motor side, and another encoder at the load side, a pulley system that allows us to amplify the torque provided by the motor, and we also have two end switches, end stop switches for calibration. Here we have the hardware schematics, so everything can be downloaded from our repository, and by acquiring all the needed components, this circuit can be assembled. The core of this hardware is the Arduino Xiao microcontroller with 48 MHz clock frequency, so it's quite robust and fast enough for haptic control. Basically we can implement two basic control modes, impedance and admittance control. Here we have an overview of the software design. It's again a modular design, and we have a class dedicated to the control of the haptic arm. So all the variables and the methods are listed here. We have a class dedicated to the sensors management, one class dedicated to the PID controller, one class dedicated to the communication, which is implemented via PWM protocol. External libraries are mostly in charge for handling different sensors, and these are connected to the main sensor class. Here you can see the control diagram for the actuation system. On the left side is without external force torque, and on the right side is with applied external torque. So when we apply external torque, the spring is partially compressed. Here we have the two diagrams corresponding to admittance or force control and impedance position control. So if we want to intuitively understand what impedance means, so you can see in this figure a boxer punching this sack, and the idea is that we could replace the physical sack with our device, replicating the reaction forces, so obstructing, impeding the movements. So finally, I would like to conclude this presentation showing you a demo. So here we have our admittance test first. So the robot will admit movements. First we have a calibration phase where we reach the endpoints of the joint. And then if we speed forward a little bit this demo, we have the interaction phase showing the admittance behavior of the robot. So the user is touching the robot, so interactingly really close, exchanging forces with the robot. And the robot is behaving as expected. And finally we have the impedance control test. And the robot is behaving as expected. And with this, I would like to conclude my presentation, leaving my contacts and highlighting that our research group is always looking for collaborations and synergies, so please feel free to reach out. Thank you for listening.